Section 3.4, Graphs of Polynomial Functions. Before we start talking about polynomial functions, we're going to start by talking about power functions. A power function is any function in the form of f of x equals kx raised to the p power. K and p are real numbers. Based on the value of p, we have other sub-classifications of power functions. For these classifications, we're also going to assume k equals 1. If p is 0, then f of x would just be 1, which we refer to as a constant function. If p is 1, we get the identity function. And as we continue increasing the powers, we get quadratic functions and cubic functions. The reciprocal function and the reciprocal squared function are also classified as power functions. 1 over x is the same as x to the negative first, while 1 over x squared is the same as x to the negative second. The square root function, cube root function, even fourth root and fifth root functions are all classified as power functions because we can always rewrite an nth root as x to the 1 over n power. Now we're going to discuss what we call the end behavior of a function. The end behavior of a function describes what a function approaches or gets closer to as x gets larger or smaller without bounds. In general, functions have two end behaviors, and we're going to represent these end behaviors with arrow notation. Because x can either get bigger or smaller, we'll have what we call the left end behavior, which occurs when x is decreasing without bounds. The notation we're going to use to represent x decreasing without bounds, or the left end behavior, is this notation here, x with an arrow pointing to negative infinity. This notation reads as x approaches negative infinity or x decreases without bounds. If x is getting larger and larger, we're discussing the right end behavior, which occurs when x is increasing without bounds. The notation we'll use to represent x increasing without bounds is x arrow infinity, where we read the infinity as approaches. With our discussion of polynomials, there's only going to be two types of end behavior. Either the function is going to increase without bounds or it's going to decrease without bounds. In other words, rise or fall. If one side of the function increases without bounds, which we'll refer to as rises, then we say f of x approaches infinity. If one side of the function decreases without bounds or falls, then f of x approaches negative infinity. F of x can approach other values other than infinity or negative infinity, and that is something we will discuss in a future section. Thanks to the arrow notation that we have listed above, we can effectively communicate the end behavior of a function with a few symbols. For example, if the left side of a graph is rising, we can write the following: as x approaches negative infinity, f of x approaches infinity. Now we're going to take a look at how to determine the end behavior of power functions in the form of f of x equals k times x to the n, where n is a positive integer. In order to determine the end behavior, first we want to figure out the sign of k. Is k positive or is k negative? If k is positive, then the right end of our power function will rise. But if k is negative, the right side will fall. After we determine the right side, we can look at whether the power is even or odd to determine what the left end will do. If our power is even, then our left end is going to do the same thing as our right end. So if our power is even, but k is positive, both ends rise, meaning f of x approaches infinity as x approaches negative or positive infinity. Or if k is negative while our power is even, both ends fall, meaning f of x approaches negative infinity as x approaches infinity or negative infinity. On the other hand, if our power is odd, then our end behaviors are going to be opposite, meaning as one rises, the other falls. So if k is positive and our power is odd, then the right end rises, which means the left end falls, meaning as x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x also approaches infinity. If k is negative and our power is odd, then the right end is going to decrease, which means our left will have to rise. So as x approaches negative infinity, f of x approaches infinity, and as x approaches infinity, f of x will approach negative infinity. Now we're going to determine the end behavior of the following power functions. First, taking a look at f of x, which equals 323,465 times x raised to the 3,246,566. When determining the end behavior, first I'm going to look at the coefficient k, and here we see our k is positive. Since k is positive, that tells me that my power function rises on the right. In other words, as x approaches infinity, f of x approaches infinity. To figure out the left end, I'm going to look at the exponent, which we can see is even. Since my power is even, that means my left and right-hand sides of my graph are going to behave the same way. Since I already know that f of x is rising on the right, that means f of x would also rise on the left. Now we'll determine the end behavior of g of x, which equals negative 5,023 times x raised to 30,212. Just like before, we're going to turn our attention to the coefficient, and we see that our coefficient this time is negative, which means our right end is going to fall, which means as x approaches infinity, f of x approaches negative infinity. For our left end behavior, we're going to look to our power. We can see that our power is positive, which means the left-hand side and the right-hand side are both going to have the same behavior. Since the right is approaching negative infinity, that means the left will also approach negative infinity. Now we'll take a look at capital F of x. Taking a look at our coefficient, we see that our coefficient is negative, so our right end will approach negative infinity, but we can see our power is odd. That means our left and right hand sides are going to have opposite behavior. Since the right is falling, that means the left will rise, which means our function will approach infinity as x approaches negative infinity. Last, we'll take a look at capital G of x, looking at our coefficient, which is 5. That is positive, which means our right end is going to rise, meaning our function approaches infinity as x approaches infinity. Looking at our exponent, we see our exponent is odd, which means our left and right ends are going to have opposite behaviors. Since the right is approaching infinity, that means the left will approach negative infinity. Now we're going to define polynomial functions. Let n be a non-negative integer A polynomial function is a function that can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and we just keep going this pattern until we get to a sub 2x squared plus a sub 1x plus a sub 0. Here, the a sub i's are all real numbers. However, a sub n cannot be 0. We can think of polynomials as the sum of power functions whose powers are all positive integers, plus some constant at the end. The a sub i's are referred to as coefficients. N, which is the highest power we see in the polynomial with a non-zero coefficient, is referred to as the degree of the polynomial. The coefficient of the x to the n, which is a sub n, is referred to as the leading coefficient. And the term a sub n x to the n, which is the term with the highest power, is referred to as the leading term. We have looked at specific polynomial functions in the past in college algebra. Degree 0 polynomials are constant functions, linear functions are examples of first-degree polynomials, and quadratic functions are examples of second-degree polynomials. Next, we're going to find the degree, leading coefficient, and end behavior of each polynomial function. If we take a look at f of x, which equals 4x to the fifth plus 2x minus 1, the degree will be the highest power we see in the polynomial. And here, we see that the highest power is 5. So f of x is a fifth-degree polynomial. The leading coefficient of our polynomial will be the coefficient of the x to the fifth term, which in our polynomial is 4. Now, we haven't quite talked about end behavior of a polynomial yet. The reason why the leading term is so important is because when our value of x starts to get really, really big or really, really small, the leading term begins to overpower the rest of the polynomial. So when x either increases or decreases without bounds, our polynomial begins to behave like the power function 4x to the fifth, and our polynomial will have the same end behavior as 4x to the fifth. Since 4 is positive, that means f of x will approach infinity, and since our power is odd, that means our end behaviors are opposite. Since the right is approaching infinity, that means the left will approach negative infinity. So to determine the end behavior of a polynomial function, all we have to do is look at the leading term to figure out how the leading term would behave. Now we're going to figure out the degree of g of x, which equals 2x to the fourth minus 3x to the sixth minus 2x squared plus 5x cubed. When looking at a polynomial, the degree does not come from the first term. Make sure you look at your terms very carefully to figure out what the highest power is. If we look very carefully, we can see that the highest power that x is raised to is the sixth power. So g of x is a sixth-degree polynomial. The leading coefficient will be the coefficient of our x to the sixth term, which here is negative 3. Now for the end behavior, we look at our leading term, negative 3x to the sixth, and our polynomial is going to have the same end behavior as the negative 3x to the sixth. Since our leading coefficient, negative 3, is negative, then g of x will fall on the right, meaning g of x will approach negative infinity. Since our power is even, that means both the right and the left will have the same behavior. So the left will also approach negative infinity. Next, we'll take a look at capital F of x. What makes capital F of x interesting is that it's factored out. Polynomials typically come in two forms. We can either have the standard form, which we see with little f and little g of x, or they can be presented in the factor form as we see here with capital F and capital G of x. To figure out the degree and the leading coefficient, we do need to identify what the leading term of f of x is. Now, one thing we could do is we could multiply out the f of x to rewrite it in the standard form and identify the leading term that way. However, because of the fourth power and the third power, this can be rather long to do. Instead, what we can do is calculate our leading term. Our leading term is going to come from the product of the leading term of each of our factors. Our first factor is negative 4, and if we look at our other factors, our first has a leading term of x, but it is raised to the fourth power. So it's as if that factor repeats 4 times, so we would have to multiply by x 4 times, or multiply by x to the fourth. Same thing goes for our next factor. Its leading term is x, and it's being raised to the third, so it will be multiplied by x to the third. So if we multiply that out, we get that the leading term would be negative 4x to the seventh, and we didn't have to expand the entire polynomial. Now we can see that the degree is 7, our leading coefficient is negative 4. Now for the end behavior, because our leading coefficient is negative, on the right, f of x will approach negative infinity. Since our degree is odd, as x approaches negative infinity, f of x will approach positive infinity because the end behaviors are opposite. Lastly, we'll turn our attention to capital G of x. Just like before, it is in factored form. So to figure out our leading coefficient, we'll first identify the leading term in each factor. In the first factor, the leading term is negative x, and the factor is being raised to the sixth power. In our second factor, the leading term is negative 3x squared, and that's being raised to the second power. When we multiply that up with our exponent properties, we get 9x to the 10th, which means our degree is 10, our leading coefficient is 9. As for our right end behavior, because our leading coefficient is positive, our g of x would approach positive infinity, and since our exponent is even, our left end behavior would also approach positive infinity. Now we've seen how the degree can impact the end behavior of a polynomial, but the degree can help us determine key characteristics of a graph of a polynomial. If f is a polynomial of degree n, then the graph of f of x has at most n x-intercepts. No matter what the degree of the polynomial is, f of x will always have exactly one y-intercept. That's because all polynomials are functions with a domain of all real numbers, and y-intercepts occur when we plug 0 into the function. The next characteristic is that our polynomial will have at most n-1 turning points, which means if we were to count all the locations where our function changes from increasing to decreasing or decreasing to increasing, which are referred to as relative extrema, we would only have at most n-1 such points. One thing to keep in mind, the keyword at most, this does not mean they have exactly n x-intercepts or n-1 turning points. If our polynomial is degree 5, it's possible that it has either 0, 1, 2, 3, 4, or 5 x-intercepts. It's also possible that it has 0, 1, 2, 3, or 4 turning points. Now we're going to find the maximum number of turning points and x-intercepts for the following polynomial functions. These 4 polynomial functions are the same polynomials that we talked about in the previous slide, so we'll copy the degrees down from the previous slide. If we look at f of x, since that is a degree 5 polynomial, then the maximum number of x-intercepts, which would be equal to the degree, is 5. But the maximum number of turning points is the degree minus 1, or 5 minus 1, which equals 4. If we take a look at g of x was a 4th degree polynomial. So the maximum number of x-intercepts is equal to the degree, which would be degree 4. The maximum number of turning points, which is the degree minus 1, which would be 4 minus 1, which is 3. Now turning our attention to capital F of x, which is a degree 7 polynomial. Since it's degree 7, the maximum number of x-intercepts is 7, and the maximum number of turning points is 7 minus 1, which is 6. Last, taking a look at capital G of x. Since that is a degree 10, then the maximum number of x-intercepts is 10, and the maximum number of turning points is 10 minus 1, which is 9. With the next few sections, we are going to study more about the x-intercepts of polynomial functions, and we're going to see why we're saying that there's at most n x-intercepts, where n is the degree of the polynomial. If you plan on taking calculus, you'll study more about how to find the turning points or relative extrema of polynomial functions and get a better understanding of why the maximum number of turning points is the degree minus 1. A particular topic of interest of polynomial functions is the study of their roots. A complex number r is called a root of a polynomial f of x if f of r equals 0. This definition seems very similar to the definition of an x-intercept, and we're going to talk about that subtle nuance in a little bit. Roots can also be referred to as solutions or zeros of a polynomial f of x, and you'll hear those terms used interchangeably. Roots, solutions, and zeros of a polynomial function all mean the same thing. Values that we can plug into the function, that'll give us 0. If r is a real number, then r is an x-intercept of f of x. So the terms roots, solutions, and zeros are more general than x-intercepts. An x-intercept of our polynomial function is a root, but not every root is a x-intercept, especially if it's imaginary. When talking about roots, we often like to track what we call the multiplicity of a root. The multiplicity of a root represents how many times that root repeats as a solution when the polynomial is factored completely into a product of linear factors. One way to interpret multiplicity of a root is basically just how many times is that root a solution, or how many times that factor corresponding to said root appears as a factor in our function. So if we consider f of x equals x minus 3 squared times x plus 1, we know that 3 and negative 1 would both be x-intercepts or roots to the polynomial. But if we think of x minus 3 squared as x minus 3 times x minus 3, we can see that 3 would appear as a solution twice. So we would say 3 has a multiplicity of 2. On the other hand, x plus 1 only appears as a factor once, so the root negative 1 would have a multiplicity of 1. So the multiplicity of a root can be determined by the power which the factor that we obtain the root from is raised to. The multiplicity of the real root tells us how the graph interacts with the x-axis at that root. If a root r is real and has a multiplicity that is odd, then the graph of f of x will cross right through the x-axis. If we take a look at this little drawing here, the blue represents the graph of a polynomial function. Notice how it's crossing right through the x-axis. That would indicate that the multiplicity of that 0 is odd. If the multiplicity of a real root is even, then the graph of f of x will touch the x-axis but not pass through it. And we refer to this as a touch and turn. If we take a look at the sketch that was just drawn, the blue graph represents a polynomial function. Notice that the x-intercept, our graph touches the x-axis but doesn't pass through it. It touches it and turns around like a ball bouncing off the ground. That characteristic indicates that that x-intercept, that real root, has an even multiplicity. We stated before that nth degree polynomials have at most x-intercepts, but when we include complex roots and when we account for multiplicities, then a polynomial of degree n will have exactly n complex roots when we count the multiplicity of each root. We'll discuss a little bit more about why this is true later, but keep in mind that nth degree polynomials do have exactly n complex roots when we account for their multiplicity. Now we're going to find the zeros of each function and state the multiplicity of each zero. When we're trying to find the zeros of our polynomial function, that means we're setting our function equal to 0 and we're solving for x. With polynomials, the most ideal situation is for our polynomial to be factored. If we look at our first example, it's already factored for us. When our polynomial is factored, we can utilize the zero factor principle to help us solve. The zero factor principle states if a product a times b equals 0, then either a equals 0 or b equals 0. Now, even though I have it written for 2 factors multiplied together to equal 0, it can be applied to 3, 4, or any number of factors being multiplied together. So to finish solving our equation, we can set each factor equal to 0. Now, the only way for a power to be 0 is if the base itself is 0. So x to the 5th equals 0 tells us x equals 0. 3x minus 2 squared equals 0 can only occur if 3x minus 2 equals 0, which means after we add 2 and divide by 3, x would have to equal 2/3. And x minus 4 equals 0 tells us x equals 4. So our zeros are x equals 0. Now, since the x equals 0 comes from the x to the fifth factor, then it will have a multiplicity of 5. Our next 0 is x to the 2/3. Since the x equals 2/3 comes from the 3x minus 2 factor, which has a power of 2, then x equals 2/3 has a multiplicity of 2. And lastly, with x equals 4, which comes from the x minus 4 factor, which does not have a power, so we assume that power is 1, then x equals 4 has a multiplicity of 1. Notice that our polynomial f of x is degree 8. If we add up all of our multiplicities, we get 8, which does match our degree. So I'm not missing any zeros, and I have all my multiplicity accounted for. Now we're going to find the zeros and their multiplicities of g of x, which equals 5x to the fifth minus 25x to the fourth plus 20x cubed. By definition, to find the zeros, that means we're setting our function equal to 0 and solve for x. Unlike the last problem, our polynomial is not factored. So we're going to proceed to factor our polynomial as far as we can. If we look very carefully, we can see that the GCF of our polynomial is 5x cubed. So we're going to factor out 5x cubed. When we factor out 5x cubed, we get x squared minus 5x plus 4 left in the parentheses. 5x cubed we can't factor any farther, but x squared minus 5x plus 4 we can factor to x minus 4 times x minus 1. Now with the zero factor principle, we set each factor equal to 0. If we solve 5x cubed equals 0, first divide both sides by 5, giving us x cubed equals 0, which means x equals 0. X minus 4 equals 0 means x equals 4. X minus 1 equals 0 means x equals 1. Our zeros, our first will be x equals 0. Since the x equals 0 comes from the x cubed factor, then it will have multiplicity 3. X equals 4 comes from the x minus 4 factor, which is raised to the first power because we don't see a power. So it has multiplicity 1. And lastly, x equals 1 will have multiplicity 1 because it comes from the x minus 1 factor, which is raised to the first power. Our polynomial, we can tell, is a fifth degree polynomial. If we add up all of our multiplicities, we do get 5. So we have found all of our zeros and the correct multiplicities. One particular challenge in finding zeros when our polynomial is written in the standard form like g of x is here is trying to figure out how to factor the polynomials. In the next few sections, we're going to come up with a technique that is going to help us find rational zeros and in turn be able to help us factor our polynomial down farther in order to find other zeros. But finding zeros in general for polynomials can be rather challenging. It is strongly recommended that you review your factoring techniques from college algebra or high school. That way you're prepared for the factoring that is to come. Now we're going to determine the multiplicity of each root based off the graph provided. If we first look at the graph on the left, we see 3 x-intercepts, and x-intercepts are real roots. So we know our roots will be x equals 1, x equals 2, and x equals 3. But what is the multiplicity of our roots? Keep in mind that our polynomial is given to be degree 6. So our total multiplicities should add up to 6. If we take a look at our graph at x equals 1, we can see that we cross through the x-axis, which tells us our multiplicity is odd. Same thing goes at x equals 3. We do cross at the x-axis, so x equals 3 should also have an odd multiplicity. At x equals 2, our graph touches the x-axis but turns around. That indicates that our multiplicity for x equals 2 is even. If we were to compare how our graph crosses at x equals 1 versus x equals 3, notice how at x equals 1, the graph crosses right through our x-axis. When our graph crosses right through the x-axis where it looks almost like a straight line, that indicates that our multiplicity of our 0 is 1. If we take a look at x equals 3, it crosses, but it almost looks like it's hesitating. It kind of has a little table right there at x equals 3. This indicates that our multiplicity is higher than 1. So it could be multiplicity 3, 5, 7, or even higher, as long as it's odd. Since we know our polynomial is degree 6, it can't be 5 or higher, because if it was degree 5, 5 plus 1 is 6, well, then I won't be able to assign x equals 2 a multiplicity. So the multiplicity of x equals 3 must be 3. Generally speaking, with odd multiplicities, the higher the multiplicity, the flatter it appears around that 0 when it crosses the x-axis. As for x equals 2, where we have the touch and turn, that could be multiplicity 2, 4, 6, 8, or so on. But if it's 4 or higher, anything that's 4 or higher plus 1 plus 3 is going to be way bigger than 6. So the only option that we have for x equals 2 is for it to have multiplicity 2. And if we add up our multiplicities, 1 plus 2 plus 3, that does equal 6. If the multiplicity of x equals 2 was higher, zeros have high even multiplicity if the touch and turn is flatter. In general, the higher the multiplicity of a 0, the flatter the graph appears around that 0. Now we're going to find the roots and their multiplicity of the graph on the right. First, finding the roots, we can see that there are 4 roots, those being located at x equals -3, x equals -2, 1, and 2. Now we'll take a look at their multiplicity. At x equals -3, since we have a touch and turn, its multiplicity is even. At x equals -2, since it crosses, it'll have odd multiplicity. Same thing goes for x equals 1. X equals 2 is another touch and turn, so another even multiplicity. Since at our x-intercepts of 1 and -2, our graph crosses straight through, we don't see that tabling effect like we saw in the last graph. The multiplicity of both -2 and 1 has to be 1. As for -3 and 2, they must each have an even multiplicity, which means their multiplicity could either be 2, 4, 6, 8, and so on and so forth. But is it possible for any one of them to have multiplicity 4? The answer would be no. If x equals -3 had multiplicity 4, then we would have 4 plus 1 plus 1, which is 6, and that would force 2 to have multiplicity 0, which is impossible. So neither of my remaining roots can have a multiplicity of 4 or higher. So that forces x equals -3 and x equals 2 to have a multiplicity of 2. 2 plus 1 plus 1 plus 2 is 6, so I have all my multiplicities accounted for. Now we're going to take a more in-depth look at the factor form of a polynomial. When we defined a polynomial earlier, that form is usually referred to as either the standard or expanded form of the polynomial. However, the standard form is not ideal for us to find the x-intercepts or roots of the polynomial. If f is a polynomial with roots r1 through rn, which are not necessarily distinct, because again, we do have multiplicity to consider, and has a leading coefficient of a, then our polynomial f of x can be written as a times x minus r1 times x minus r2, all the way down to x minus rn. Now, we often do try to clean this up a bit. When we account for the multiplicity of roots, we'll write x minus r to a power to help us simplify. From the factor form, it's very easy to find an equation for a polynomial based on its graph. Here, we're going to write the equation of the graph that we took a look at in the last example. Since this is the same graph we looked at in the previous example, we'll just quickly jot down what the roots are and their multiplicity. So from here, we can start writing the equation of our polynomial in the factor form. The only thing we don't know yet is the leading coefficient. Since we don't know the leading coefficient, we'll keep a for our leading coefficient and then proceed to write x minus our roots. So we have x minus -3, but since it has multiplicity 2, this factor would appear twice. Then x minus -2, x minus 1, x minus 2, but because it has multiplicity 2, we'll write x minus 2 twice. But we can do a little bit of cleaning up. We know that when we subtract a negative, that becomes addition. And I also have the same factor being multiplied with itself, so we can use exponents to help us condense that a little bit more. So x minus -3 becomes x plus 3. And since I have two such factors, I'm going to write it as x plus 3 squared. X minus -2 becomes x plus 2, then x minus 1. And with the x minus 2, since there's two of them, I'm going to write it as x minus 2 squared. Now from here, we need to figure out what a is. In order to figure out the value of a, we need to identify another point on the graph that our graph will pass through. And here, our graph does pass through the point 0, 3. Now here I'm using the y-intercept because if I can plug in 0, that's going to be very easy to work with. However, you don't necessarily have to work with the y-intercept. You can pick any point on the graph as long as it's not an x-intercept. But what the point tells me is that f of 0 equals 3. So if I plug 0 into my equation, I should have 3 as the answer. Now I've set up an equation that will allow me to solve for a. If we simplify the right-hand side by punching the numbers into a calculator, our right-hand side becomes -72a. Then we can divide both sides by -72, and we get a equals -1/24. A was the last piece of information we needed to complete our equation. So the equation of our graph in factored form is f of x equals -1/24 times x plus 3 squared times x plus 2 times x minus 1 times x minus 2 squared. As stated before, one of the big challenges to polynomial functions is trying to find their x-intercepts or their roots. Because of the difficulty, oftentimes we'll just be happy if we can figure out roughly where an x-intercept or a root would occur. One of the theorems that help us locate roughly where a root could be is the intermediate value theorem. The intermediate value theorem states the following. Let f be a polynomial function. If f of a and f of b have opposite signs, then there exists at least one value c between a and b such that f of c equals 0. To understand why that is true, let's say this red line represents the x-axis, and we have 2 points that we know are on the graph of our polynomial, one point below the x-axis, the other point above the x-axis. So for one of these points, they would have a function value that's positive, while the other will have a function value that's negative. One of the key characteristics of the graphs of polynomials is that their graphs are what we call continuous, meaning when we draw the graph of polynomials, we can do so without ever lifting our pencil off the paper. So the challenge becomes, is it possible for me to connect these two dots without lifting my pencil and not crossing the red line if that red line stretches forever? The answer is no. No matter how I draw my graph to connect these 2 points, I must pass this red line. So wherever my graph will cross, that would be where an x-intercept occurs. One thing to note, if f of a and f of b have the same sign, then the intermediate value theorem cannot apply. The reason being is it's impossible to make a conclusion based off of that information. If we take a look at the 2 graphs that I've drawn, the one on the left we can clearly tell has no x-intercept, but both points do lie above the x-axis, meaning our function value at both those points will have the same sign. But if we also look on the graph to the right, we see the same thing where both points lie above the x-axis. But we can see that our function does have an x-intercept. So when both values of our function have the same sign, we can't draw any conclusion. Our function may have an x-intercept between the 2 points, or it may not. We don't know for sure. Now we're going to determine if each polynomial has a real solution within the given interval. Here they're not asking us to find what the real zeros are. In fact, if we tried to find the real zeros here with what we know so far, we wouldn't be able to because there's no way to nicely factor 3x cubed minus 8x plus 1 with the skills that we have so far. So we'll resort to the intermediate value theorem to see if there at the very least exists a zero between -3 and -1 or -3 and 1. First, we'll take a look at -3 and -1. In order to apply the intermediate value theorem, we need to take the endpoints of our interval and plug them into our function. If we plug in -3, we get -56. If we plug in -1, we get 6. Since the sign of f of -3 and f of -1 are opposites, then we can make the conclusion by intermediate value theorem that there is a zero between -3 and -1. So, by the intermediate value theorem, f of x does have a real zero within -3 and -1. From there, we could use other techniques to try to shrink the interval that our zero would be located, or use what we call numerics techniques to try to approximate what the zero would be, perhaps even using technology to help out. Now we're going to take a look at the same function, but we're going to change the interval to -3 and 1, to see if intermediate value theorem tells us there'll be a 0 in that interval. So just like before, we're going to plug the endpoints of our interval into our function. We've already plugged in -3 before. We know from the previous example that is -56. When we plug in 1, we get -4. Here, -56 and -4 have the same sign. Now, does that mean that there is no real 0 in the interval -3 to 1? No. This simply means that the intermediate value theorem cannot be applied here. In fact, it would be wrong to say that -3 and 1 did not contain a real 0. That's because -3, -1 does fit within the interval -3 to 1. So we know a 0 does exist. It's just that the intermediate value theorem can't be applied to tell us that there's a 0 in between -3 and 1.